Hello everyone and thanks for joining. My name is Neşet Ünver Akmandor and today I'm going to present our work titled Reactive Nonlinear MPC for Multimodal Motion Planning via Deep Reinforcement Learning, or as we call it, Re4MPC. This work focuses on integrating deep reinforcement learning with nonlinear MPC for more efficient and adaptive motion planning. Now let's start with the motivation behind our approach. Motion planning in dynamic environments has always been a difficult problem in robotics. The challenge comes from two main factors. First, the robot must constantly adapt to changes around it, for example, moving obstacles, changes in terrain, or other unexpected events. Second, it has to plan motions that the robot can physically execute, respecting its mechanical limits and motion capabilities. To produce high-quality trajectories, the robot has to solve complex optimization problems under strict time limits. Even with modern GPUs and parallel computing, this remains very demanding. When we deal with robots to have many degrees of freedom, such as mobile manipulators or humanoids, the computational load becomes even greater. In real-world scenarios, where decisions must be made in milliseconds, this can limit the robot's ability to respond effectively and safely. In motion planning, there is often a trade-off while defining robot models. Complex models include detailed kinematics or dynamics. They are more accurate and can handle a wider variety of conditions, but they require more computation time. Simplified models ignore some of this detail, so they are faster to compute but less precise. Choosing the right model for each situation is not simple. If we always use the complex model, we may run out of time before completing a computation. If we always use the simplified model, we may fail in situations that require precise control. The best choice depends on the task, the robot's current state, and the complexity of the environment. One of the main goals of our work is to make this decision learnable, means letting the trained policy switch between models as needed without manually designed conditions. To address these challenges, we propose a reactive multimodal nonlinear MPC pipeline designed to efficiently compute trajectories for robots with high degree of freedom dynamic models. We use a deep reinforcement learning approach to train a policy network that adapts NMPC settings based on the robot's state and task. At each control cycle, the trained policy provides the robot model to use, terminal and intermediate cost weights, constraints, and the target state at the end of the horizon. An MPC then uses this information to iteratively compute a trajectory which is executed as control commands. The policy is trained using observation action reward data collected from simulations. Adapting partially observable Markov decision process formulation, where the robot's full state is not directly observable, we designed the observation space to include information that can reliably obtained from sensors. This includes the goal position, which is determined relative to robot's coordinate frame. For each occupancy object, the observation includes its position and volume information. This allows the policy to reason about both where the object is and how large it is when making decisions. For the self-collision observation, we calculate the minimum distances between relevant pairs of the robot legs. We also include the mobile base's lateral and angular velocities, as well as the arm joints positions and angular velocities. Together, these provide a complete picture of the robot's current configuration and motion. At each RL step, the action, either continuous or discrete, defines how an MPC will be formulated. Both formats specify subspaces for the robot model, constraint, and target. As a proof of concept, we consider three different models of a custom-designed mobile manipulator platform. For the continuous action space, the model index is determined by threshold values within the model subspace. For constraints, we compare the corresponding action value to a threshold to decide whether a specific constraint will be included in the NMPC formulation. The first element in the target space indicates whether the target is the final goal or an intermediate subgoal. The remaining elements define the 3D position and orientation of the target. For discrete actions, we divide the model, constraint, and target subspaces into bins, and assign each possible combination to an action index. This way, a single action index represents a complete NMPC configuration. The reward function includes both terminal and intermediate components. Terminal rewards or penalties occur when the goal is reached, the robot moves out of bounds, a self or external collision happens, the robot rolls over, or the maximum time step is reached. External collisions are detected by sampling points on actuated links and checking distances to obstacles and the ground. Self-collisions are detected when any link pair is closer than a safety threshold. At each RL iteration, the step reward is calculated as a weighted sum of multiple reward terms. To encourage the use of simpler models when possible, we include a constant penalty based on the degrees of freedom of the chosen model. A distance-based reward encourages the end effector to move closer to the goal and penalizes moving away from it. We also include a step target reward to promote the use of intermediate sub-targets rather than going directly to the final goal. When only the arm is moving, the reward is based on mechanical stability using the center of mass position. We measure the difference between the desired and actual center of mass over the action horizon, then reward or penalize based on whether it stays within a stability threshold. When only the base is moving, the target reward is similar to the goal reward, but uses sub-goal pose instead of the final goal. This sub-goal is positioned partway along the straight line toward the goal, helping the robot progress in smoother steps. Although moving towards effective sub-targets improve the performance of the motion planning, prematurely reaching them within the action horizon have a negative effect on the control flow. In order to avoid unnecessary interruptions and improve the harmony of consecutive actions, we introduce a penalization term when the target is reached. In the design of our training and testing environments, our primary goal is to demonstrate that our trained approach effectively adapts its NMPC formulation. This includes switching its system model and assigning feasible subgoals based on the current state. While robustness analysis of the trained policy and its generalization to unseen environments is beyond the scope of our work, these aspects could be enhanced by training the policy until convergence across various environments and tasks. Within our focused context, we develop a simple simulation environment that includes a conveyor belt and the bugs to be picked up. At the start of each episode, the robot's base pose is randomly initialized within the orange area. While we set the end effector goal to a fixed orientation, its position is randomized within the purple area on the conveyor belt surface. We train the policy network using 3 different DRL algorithms: proximal policy optimization, soft actor critic, and deep queue network. We adopt continuous action space representation for PPO and SAC, and discrete action space for the DQN. We also create ablation versions of each method without the target reward to study its effect. The results show that after 15K episodes, which is roughly 100 and 115K time steps, all variants of our proposed algorithm start to receive positive reward values. Based on the plot, we can observe that both SAC variants receive the highest rewards, while the one without the target reward converges fastest among all variants. Training curves of both PPO variants are similar. However, as expected, the one trained with the target reward converges faster than the other. Similar to PPO, including the target reward also helps DQN improve earlier in training. Also, DQN's performance is similar to PPO's, but it is more sensitive when resuming training from saved models, as you can observe the steep training curves, which we plan to investigate further. To obtain these results, we didn't perform hyperparameter tuning, so better results could likely be achieved with some tuning methodologies. We evaluated our proposed model across 108 different configurations within the same environment. Each configuration was run 5 times to ensure robustness of the results. The results show success rates for the baseline and all Re4MPC variants. We measured the performance at multiple training stages from 20K to 100K time steps. For the baseline, we used the SLQ method to compute whole body trajectories with the goalpost set as MPC target for all iterations. From the results, the SAC variant without the target reward performs best, exceeding the baseline by about 20% in success rate after just 20K time steps in training. By 100K time steps, all Re4MPC variants achieve higher success rates and fewer failures than the baseline method. In terms of success, rollover, and collision metrics, Re4MPC consistently performs better than the baseline method. One of the clear benefits of Re4MPC is reducing computation time without losing performance. When the policy decides to use only the base model, the computation time per step is reduced by more than half compared to the whole body MPC. This is important because in real-time control in a dynamic setting, even a small time saving can significantly improve the overall performance. The agent learns through training that in many cases, moving the base into a convenient position first is both faster and more reliable. It keeps the more complex whole body planning for situations where it is really necessary. This balance between speed and precision is what makes the approach scalable to a more complicated environments. Another way to look at our result is through the complexity of the models chosen during planning. Our experiments show that Re4MPC significantly reduces reliance on the whole body model. When trained with PPO in a continuous action space, the average model complexity decreases by about 56%. And with DQN in a discrete action space, the reduction reaches about 71%. This shift toward the reduced order models directly lowers average computation time and also decreases the risk of instability. As discussed in our analysis, one of the common failure modes in the baseline was rollovers caused by high arm momentum when moving aggressively toward the goal. By switching to base-only or arm-only models when appropriate, Re4MPC avoids many of these rollovers, leading to higher success rates without adding extra constraints or penalties. Another important result is how the policy decides between going straight to the goal or creating intermediate sub-goals. In many cases, especially with discrete action space, the policy chooses to set a sub-goal first. This approach leads to smoother and more practical motion, especially in cluttered environments. For example, instead of stretching the arm from an inconvenient position, the robot might first move the base closer to the goal, then use the arm to finish the task. This reduces the chance of collisions and improves stability. Our results show that agents trained with DQN increase sub-goal generation by over 70%. This shows that the learned strategies can match what an experienced human operator would intuitively do, breaking a complex movement into smaller, safer steps. From the ablation study, we verified that including the target reward leads to faster training, higher success rates, less use of complex model, and more frequent sub-goal generation. The open source implementation of Re4MPC, along with datasets and experimental details, is available at the link shown. Thank you for your time and interest.